now matches the way we use the survey WPU indices for apportionment purposes. We adjust the survey WPU, as I'll show, for a couple of different factors. And up until this year, I had not been doing that on the input side of the data set. I did so, and you'll see that effect actually is also relatively minor. So I've got three broad sections to go through. One is simply data and observations, model-free. Get an idea yourself where we are. Then I'll talk about the model. It uses all that data and the observations. And I got a third section that kind of talks about a variety of factors, sort of further observations. Okay, so I do like to sort of highlight recent history of removals and trends from the fishery. This is what all fisheries combined take out of the stock. I started this at 2004, which was actually the high point in the history of the fishery. We took out just shy of 100 million pounds that year, and ever since then we've come tumbling downwards. This graph actually shows the different type of removals by year, and then I have percentages there that illustrate the decline each year in both total removals, indicated by T, and commercial removals by C. And I'll be more of this in a second. Of course, the trends differ by area, depending on what's happening in each area. And as we've changed assessments, we've gone from various forms of assessments, switching over from closed area to coastwide and so on. So some of these slides are just for your informational purposes. So you have them at your fingertips, of course, in the blue book. So this illustrates it by area. You can see we've come down pretty steadily in most areas. There's been a few exceptions. But put this in the biggest, oh no, before I get to that, this is one other aspect of the removals that is influential and I think is responsible for a lot of discussion and in fact is leading to a workshop that we've been assigned to run come April, and that is the bycatch, the unintended capture of halibut in non-directed fisheries. There's two sizes of that, of course. There's the U32 component, which I'll talk about here in a second, and the O32 component. The O32 component is simply treated the same as if it were captured by a directed fishery. It's taken off the top. This past year it was 4.044 million pounds. I indicate that there in the bottom left-hand corner. That, of course, is simply lost to the other directed fisheries. But the U32 bycatch is somewhat different. That's smaller, younger fish who are not then entering the population or removed from the population prior to being captured by the directed fisheries. These estimates here are the ones we obtained from NIMS. Part of the workshop is to determine how accurate these are, and the second part is to determine how we incorporate these into the management. But this side summarizes the impact on the stock of this U32 bycatch. The coastwide capture of U32 halibut was last year 6.3 million pounds. The graph there shows in the green bars year by year the estimated U32 bycatch in millions of pounds. It's been stable around 6 to 7 million pounds. The black dots above each of those bars is the estimated loss at our current target harvest rates of the yield to the directed fisheries, principally sport, subsistence, and commercial. And so because the black dots are higher than the green bars, indicates that for each pound of U32 bycatch, the loss to the directed fisheries is actually more than a pound. It's on the average of 1.2 pounds. Now, this is on a coastwide basis. This is not, the yield loss differs by area. It's dependent on a number of factors. The size of the U32 bycatch when it's taken, the size and age of fish in different areas. Juan Valero and I have done a couple of papers in past years trying to estimate the area-specific impacts of that. I'm not doing anything. I'm just sort of giving a broad-scale picture of the yield loss. But even perhaps more problematic than the loss of yield to the commercial fisheries is the impact on spawning biomass. We are, as you know, E-bio is coming down strongly, as are the catch limits. The spawning biomass is also coming down. And we estimate that for each pound of U32 bycatch taken, the loss to the spawning population, the female spawning biomass, is on the order of 2.2 pounds. And that's because once a female is taken out, if it had been left in the water, it would have contributed to spawning biomass in multiple years. before taken by a directed fishery. So that's why the spawning biomass loss is quite a bit larger than the loss to the exploitable biomass or to the directed catch. Second here, it's trying to get. Well, here we go. All right, so just to orient us here, because I think it's important to put where we are in context, and as I mentioned, I'm trying to point out how we got here and where we are. And so this is, as you've seen, I think, from Juan and other times, this is the long history going back to the beginning of the halibut fishery and total removals. And I've simply broken down here into commercial and non-commercial. We don't have estimates of non-commercial prior to the first estimate of bycatch in the early 60s. So you see up until the late 70s, it was rather simplistic modeling was done of the halibut populations. Monitoring trends in CPUE using VPA-type models. And then we began the modern era of modeling. Cajun, which was developed at the Halibut Commission, was used up until from like 82 to 1995. Cajun was abandoned for the very reason we're having problems with the model now, retrospective issues. The model would be run, and then subsequent runs would produce different estimates of biomass for the estimates of the available quotas. Part of that issue, of course, and I'll touch on a couple more slides, is what drives selectivity. As Juan noted, selectivity and catchability are huge issues in fisheries modeling, and they certainly affect the halibut population models. So for a number of years then, we tried a variety of models. It was called the selectivity wars. I think is what Bill Clark called it. We fit models both with selectivity based on age and based on length. And in the parentheses there, I have the average total removals during the periods when the different models were being used. The high point of the removals came during the era of the closed area models, and we've heard questions, why don't we go back to those days of the closed area models? Well, I think looking at this graph, you'd have to sort of come home with the fact that that was the best science at the time, but the removal levels generated by those models at that time were extremely high, and we've been working our way downwards from those ever since. I indicate here the 7-year decline since 2004. It really wasn't until 2007 when the first catch limit recommendations were based on the coastwide model. But anyway, we've been coming down sharply from there. I highlight on the last one in red the recommendations that you're going to hear about for 2012, and say this it's been not great fun working these downwards. So this is our gold standard for estimates of the status of exploitable biomass. We measure on our survey the weight of all fish over 32-inch captured in our survey, and that weight is measured per 100 hooks per standard skate, done on each of our regulatory areas, except for 4CDE. Usually I present slides of 4CDE, but it takes several slides to explain it. It's in the blue book. So 4CDE is assembled from a bunch of different time series involving some trawl data. I won't get that, but anyway, that works together to produce a similar type plot as the other areas. And so you see here the trends and the standard errors for the each year's estimates of the catch rate of halibut on our survey. And of course, the coastwide total has shown an unarrested decline from the beginning of the survey in 1996. Occasional change in that trajectory, but overall continuation. This year, the decline was just 5%, but that follows on the footsteps of 15% decline last year. We've had, though, reversal in some trends. Area 2, in particular, was the area that we cut removals the most following this switch from the closed area to the coastwide model. That's indicated in each of these graphs by a vertical, purple, I guess, dashed line, so you can see exactly when we made the switch. And I mean, cutting those removals that much in Area 2 had the anticipated effect. Area 4, we'd also seen for that some arrest in that decline, although for a different reason. I'll talk about this a bit later, but those areas had been designated as areas of particular concern and had cut harvest rates. We did the same thing in Area 3B last year, because 3B of all the areas has certainly shown the greatest decline from the early days relative to where it is now. But that area continues its decline, and 3A had remained relatively stable relative to the other areas until about 4 years ago. They then saw a sequence of strong declines until this year, 1 year, perhaps aberration, perhaps not. They actually had an increase from last year. One thing I do want to just note about these is that keep in the back of your mind for some of these areas, particularly 3B and up to area 4CDE, the beginning of the time series was an era when those areas were relatively lightly exploited relative to areas 2 and 3A. Areas 2 to 3A have been fully exploited, 50, 70 years. There was fishing in 3B and areas 4, but not at a high level. And once we imposed the surveys, we sort of unleashed full-on fisheries there, noting at the time that the removals at those levels were not sustainable. They would come down. Perhaps easier said than done in hindsight. But the decline as large as you've seen in 3Bs, it's a little bit different than if we'd have seen a decline that large in area 2B, for instance, which had been fully exploited for such a long time. The next slide just takes these same time series and scales them all to the same vertical axis, so you get some idea of how different early catch rates were among areas and how similar that they are now. These are all scaled out to a value of 0 to 500. You get an idea here of relative catch rates on our survey among different areas. I don't have any more to say. I just want to just give you an illustration of that. This is a different set of data from our survey. This compares not the weight of halibut that are caught, of 032 halibut. This looks at the catch rate of numbers of halibut that are taken on the survey. The purple is the total number of halibut caught, and then the two lines below the purple are 032 in blue and U32 in red. And see, just like 032 WPUE, we've had an ongoing decline in numbers caught, particularly in the 032 component. The U32 components remain relatively level, slight increases in some area. The highest catch rates of U32 animals in 3B, for instance, which has had that really strong decline in WPUE of 032 animals, but it's had an actually increase in the U32 component. But there's not an indication here of a whole lot of smaller animals caught on this, and that kind of leads me to my next two slides here. And this is a key to probably what we more discussions about what drives selectivity to the gear, both on our survey and in the commercial fishery. These are the catch rates for 8, 9, 10, 11, 12-year-old females since 2000 on our survey. So the low one is the average number of age 8 halibut, female halibut caught per skate. And then each line goes up as the catch of 8 through 12. So among these 5 ages, there's somewhere between a level and a slightly increasing trend in the catch numbers. So selectivity, what you assume about selectivity would imply different things about the number of those animals that are in the population. You catch a certain number. What affects their capture by the gear? And so before I answer that question, this is a smooth illustration of the length at age of each of those 5 age class of females. So they were, take age 8 females, they were on average about 80 centimeters in 2000. They're now about 72, 73 centimeters. The age 12s were 98 centimeters or so. They're now down to about 91 centimeters. So go back to this one here. If selectivity is driven by age, it doesn't matter how big they are, it only matters how old they are, then these catch numbers would imply there's pretty much a similar number of females out there each year over the past several years, because the catch numbers are about the same, and if they're driven, and if your catch is proportional to the number that are out there, then that's the implication. The assessment that we do now, on the basis of work that principally Bill Clark did and published in a RARA paper, we made the jump to the assumption that selectivity is driven by the size of halibut, not by their age. And so when you have a stable number of halibut being caught, or slightly increased, but the selectivity is lower, then it implies there's more in the population than there was the previous year. You catch the same number, but they're smaller, so you should catch fewer because selectivity is lower. So that's kind of one of the things that's going on in the assessment. We see this stable number, but they're smaller. So we're catching the same number, but selectivity is lower. Does that mean there's more out there? Okay, slide here. Okay, so this is a slide I think I introduced last year, the year before. There's 2 of these. This is a means of comparing the relative change in total removed from the population and the change in survey WPUE by area and coastwide. So most of these plots, removals are indicated by the black lines and survey WPUE by the purple line. All these time series are standardized to a value of 100 for the period 1997 to 1999. So you average what the WPUE was in those 3 years, you average what the removals were in those 3 years, set that to a value of 100, and then each year subsequent is some percentage of that value that it was in that average period. And so on a coastwide basis, if you look at the bottom right-hand corner, it shows that survey WPUE, as of this year, was at 34% of its average value for the period 97 to 99. Total removals, however, are at 60%. So the WPUE has come down quite a bit more than the removals had. In a fully exploited system where you're targeting a constant harvest rate, those would move in parallel. Now, there's a little bit of a, as I mentioned earlier, a few slides ago, in fact, we weren't starting at a fully exploited system. Areas 3B and 4A, 4CDE were fished in a relatively lightly exploited state. You had a higher WPUE here than would be expected in a fully exploited state. So this drop is a bit exaggerated, if you will, in that regard, though how much, is not certain. The next slide is going to be looking at what's gone on since we switched to the coastwide model in 2006. So here I did the same sort of thing, but I standardized the time series, instead of from 97 to 99, to the 3 years prior to the switch to the coastwide model in 2006. So here the value of 100 is for the 2003 to 2005 time period. And the vertical dashed line is a switch from closed area to the coastwide model. And removals have tracked survey WPUE from that point forward. And that's kind of how we've made our recommendations each year. Is the model has basically followed that declining trend in WPUE. We've made recommendations on that, and to a large part they've been accepted. But as Juan's illustration or his presentation showed, the target harvest rates were likely too high during that period. We'd had, as I showed, the removals were at 90 to 100 million pounds at that point. And by maintaining a constant decrease parallel with the WPUE, we basically maintain those too high harvest rates up until the present. But I guess the other point is this, is that we follow the advice of the assessment model in terms of tracking the WPUE. This is a similar plot to the survey WPUE, only for the commercial aspect of this. Of course, the commercial fisheries can move around. They can chase the fish. They have declines in catch rate. They can move. But despite that ability, the commercial WPUE has also come down rather consistently over the past 10 to 15 years. Not as strongly as the survey, but still, it's done so, with noted exceptions. I mean, 2B obviously looks at this and says things are better than ever, since they this year had their highest commercial WPUE going back to at least the changeover from the J hooks to C hooks in the early 80s. One point I want to note here, because it did affect the assessment this year, and I'll talk about, is you notice the total panel in the bottom right-hand corner has two values here. By the way, each of those percentages is just simply the year-to-year change from 2010 to 2011. So the bottom right-hand corner shows two values. The plus 1% is the illustrated change between the last two data points. So right now, the estimate of this year's commercial WPUE is actually up 1% from the current estimate of last year's commercial WPUE. But at the time I did this talk last year, that next to last point wasn't where it's shown. It was actually higher than the 2011 value. That's because every year I do the assessment, at some point I've got to lock the data set, so I get at least 3 weeks to do the assessment. Well, there's still data out there. It's in the mail. We haven't had time to enter it yet, so there are things going on. And so when we got that full data set, and I reran it this year, what I do first thing before I add any new data that's to check the effect of having now a fully completed previous year's data set. It dropped that value by 5% and had actually a little bit larger effect than that on the assessment. So while the WPUE at this point indicates that there's an increase, that may not hold. I will note that 1-year decline was bigger than we'd ever seen in other years. I checked this then, how big had been the change from the early lock data set to the final data set, and it had never been anywhere near as large. So something happened this past year, and we're looking into why exactly it occurred. But obviously it's not ideal, but it is a factor each year though, and it's sort of what we call a revision aspect to the assessment as opposed to the retrospection, which you heard about and we'll hear more about. This again just takes all those same time series and plots them on a common scale. Here they're all scaled from 0 to 800 to account for the largest catch rates in some of the areas, like 3B and 4C in the early days. And then you can see that there's been the commercial catch rates are much more similar along different areas than they were early on, say in the mid-90s. And even though you can't tell from here, Area 2C actually had the largest commercial. Oh, I'm sorry, no, it was the survey. So the survey WPUE was higher in 2C than it had been for the first time. Area 3A still has the highest commercial WPUE, and that's been consistent now ever since the western areas have come down from those early times. I just want to highlight here some factors about the catches that we take, and part of the early rationale for considering moving or changing the size limit. This is an illustration of the difference in the age composition of the catches between our survey, shown on the left, and the commercial catch on the right. I want to note the survey catch is actually observed. We sex the animals. We know for sure what's female and what's male. The commercial is done on a statistical basis where we estimate the sex composition at length, the age composition and sex composition at length to determine the commercial. We think it's pretty good, but just want to note that there's a bit of a model component to the breakdown of the commercial catch composition. The survey is fully observed and measured. So what this shows then is that for the survey, about 54% of the catch is female, about 46% is male. That's by number. I didn't have time to assemble the numbers by weight. This is a suggestion near the end. It's be more like 60% female and 40% male by weight. And the most commonly caught animal in our survey now is a 12-year-old female with 9.3% by number. You contrast that with the estimated sex and age composition of the commercial catch, and this is what we mentioned is predominantly a female fishery. By number, we estimate about 76% of the commercial catch is females, and it'd be like 80+% by weight. Again, the most common animal is an age 12 female, and so it's this difference between these two different compositions that suggested maybe we should consider lowering the size limit, because as you move from the current commercial size limit towards no size limit, you would be presumably, assuming selectivity operated the same manner and the fisheries operated the same manner, you'd shift from the one pattern to the other. But as Juan illustrated, there's a lot of other factors to consider: the impact on the female spawning biomass, the number of animals you'd handle, the tighter control required on harvest rate, and so on. That makes it no slam dunk at all, and at best it would be a zero-sum game. And so there's no compelling reason to move forward in that regard. We also just want to compare among regions. This shows the estimated female age composition in the commercial catch by area. So we're just contrasting or comparing the different regulatory areas. And so we have here in the red bars now just showing the female, the proportion female in the catch by area. The green curve is common to each of the plots. That's the maturity at age. So the green line reaches a value of 50% at about age 13, meaning that at 13 years of age, half of the females at that age are contributing to spawning biomass. And so, obviously, as Juan noted, you'd like to allow females opportunities to spawn before they're removed. And to the extent that the red bars are to the right of the green curve, that's happening more so than in the case where the red bars are to the left of the green curve. And why is that important? Differences among areas, well, just from first principles, if the females in a particular area are responsible for producing eventual recruits to that area, then you want to have a wider, broader, older age distribution of females so that you are ensuring the continuation of that population and recruits to that area. So we've noted that there's long been some difference in these, and it was another one of the arguments kind of for shifting from the closed area to the coastwide models to bring down those harvest rates in Area 2 and increase those average size, those average ages in the population. There has been actually a slight increase in Area 2, illustrated here. It's not been great yet, but it's on the order of 0.1 to 0.2 to 0.3 years, which is sizable when it's spread across thousands of animals in the catch. Another thing that I like to look at is the trends in the average ages and average weights of the animals, both in our survey as well in the commercial catches. So on the top two plots are for the survey, the bottom two plots are for the commercial catches. The vertical ones are ages on the left and weights on the right. So the ages, what we're looking for there is how the average age in the catches trends over time. In the sense of if that's kind of stable, then I would take that almost as a good sign. It's sort of stabilization, that if you were to have all of a sudden all young fish in the catch, that might mean, it could mean one of two things. It can mean that there's a really huge increase in the recruitment of young fish, or it's the disappearance of older fish. And conversely, if the other way goes around, you had only old fish and no young fish, it's not going to mean you're catching more fish, it's older fish. It's going to mean you have fewer young fish. So to the extent that these are relatively parallel means that I think that is a relatively good sign. The right-hand plots are the average across ages, the average weight in the catches, and that's simply the demonstration of the ongoing decline in size at age that is not arrested, isn't really showing signs of arresting yet. And I don't have a plot of it here, but I actually got the data from the trawl surveys as well and looked at even younger fish, because the trawl surveys get fish down to 4 years old, and the size at age of even 4- and 5-year-old halibut is declining, is declining, continuing to decline. And those animals have experienced no fishing mortality to speak of other than as trawl bycatch. So just an illustration of some of the data from the NIMS trawl survey. Every year the NIMS does a standard grid in the eastern Bering Sea, and this plot simply shows for this year the catch rate of all halibut that they capture in their trawl, all sizes. The size and color of the dots convey similar information. The color is related to the colored bar on the bottom, and you can see that's kilograms per square kilometer. You get an idea of where the highest densities of halibut are, typically in the closed area, close to commercial halibut fishing, that is. And then you can see it tends to decrease up to the northwest, and there's actually quite little out in the further northwest. Last year, for the first time, NIMS had done a survey in the orange outlined area, northern Bering Sea survey. I don't know if they'll do that again, but we were able to use that data and found quite low densities out there. There are some halibut out there, and we account for them, but relatively low densities compared to the southern part. This year, NIMS also surveyed the Gulf of Alaska. They lately have been alternating between the Aleutian Islands and the Gulf of Alaska. So this shows the catch rates of halibut, again, all sizes, all ages, in Area 3B. To get some sense of where they're capturing them. And then next one shows Area 3A, same thing. Rather paucity of halibut in the central 3A area here. It's more pronounced than occurs in our setline survey, though our setline survey also encounters much higher numbers around Kodiak Island and in the central Gulf area. One thing that did occur this year is the different vessels were used for here. So these numbers for Gulf of Alaska in the trawl survey were down. You'll see that later on, quite a bit from the last time they did the survey 2 years ago. And I was unable to counter anything in the operations of the trawls, of the vessels, that would account for this strong decline in Area 3A. Oh, and then Area 2C, it's not particularly conducive to trawling for halibut, I suspect. And so I'm pretty certain this is an underestimate of halibut density in Area 2C. You can see they're restricted to just a couple locations. All the areas with black X's, if you can see those, are trawl stations with no capture of halibut at those stations. And that was true of the other plots as well. So now that's a sort of a broad view of the data that we collect each year and examine. Now the assessment model this data is fed into. First, as I noted, I assemble a coastwide data set now. There's only a single model. It's for the coastwide population, but we collect data by regulatory area. So all those data parts are put together to form a coastwide data set, and it's done by weighting them, either by the relative density or by the amount of bottom area. What I had not been doing was adjusting the survey WPUEs or survey NPUEs for these other adjustments that we were using for apportionment purposes. And so to be thorough, I did that this year. So there's two kinds of adjustments that are done to survey WPUE for apportionment and now for constructing the coastwide data set. One is what we call the hook adjustment, and that is competition for baits on the survey. There are different densities, different predators in different areas that are competing for those baits once they hit the bottom. And in areas where there are more aggressive or higher density of the predators, they'll steal those baits before halibut can get to them. And so that kind of is a catchability effect. And so we devised a method, Bill Clark actually did, and it was actually duplicated by some UBC researchers, which adjusts the WPUE for that effect. So the left-hand plot here simply shows the adjustment value that's computed for each area, and you get the range of variability. Each of those vertical box and whisker plots shows the range of adjustment factors for the period 96 to 2011. Area 2A always has an adjustment value above 1, and that reflects the fact that I guess it's hagfish steal the baits really quickly in Area 2A, so there's fewer baits actually effectively fishing for the halibut. Area 4 in general has the opposite case. There are fewer bait stealers there, and so we tend to adjust their WPUE downwards, since they have effectively more fishing effort relative to the other areas. The center of the range typically is a value around 1, but there are departures from that. In particular, Area 3B the last few years has had quite large upward adjustments, and it has been a factor in their apportionments relative to their decline in their catch rates. The other adjustment has to do with the timing of our survey relative to when the commercial, not just commercial, when total removals take place. Our survey is designed to measure e-bio, but if a lot of the e-bio has been removed prior to the survey, then that should be accounted for. If one area, most of the total removals were taken before the survey got there, then the survey is measuring something different than the case where our survey comes in before the removals take place. However, at our target harvest rate anyway, the adjustment's very minor relative to the hook adjustment, except in Area 2A. Sorry, I didn't correct this figure. There's some missing labels on here. Area 2A is the one to the far right. So you can see the two different values. Then you put them in combination, and you get the bottom plot there where you get the actual annually applied adjustment factors for each area, for CDE on the left and over to 2A on the far right. So how that affects the survey WPUE is shown here. The raw values, which you saw earlier in the time series, but without the standard errors shown here, are shown by the black squares. The adjusted WPUE values, that is adjusted for the hook competition and survey timing, are shown as red circles. So each of those is simply the raw WPUE multiplied by the adjustment factor. And then for apportionment purposes, though not for the weighting of the input data set, we take a 3-year reverse weighted average. So we use a backwards weighting scheme of 75%, 20%, and 5% to get a working value then that is used for that area's estimated catch rate that's then weighted by bottom area to determine its apportionment. So I'm not going to be talking about apportionment again on this. I've talked about it a lot in the past. This is what we've settled on doing, and just give you an indication of how the apportionment fraction for each area is determined. That's what's given in this slide. The other factor that affects both the construction of the coastwide data set and the apportionment is the definition of bottom area that's used. In the early days, we used the definition of 0 to 300 meters. Now we use a definition of 0 to 400 meters. But in fact, our survey operates in 20 to 275, I'm sorry, I say meters, I mean fathoms. 0 to 300, no, I do mean fathoms. Yeah, I mean fathoms. 0 to 300 fathoms, then 0 to 400. Now our survey takes place in 20 to 275 fathoms. Well, the amount of bottom area in each area differs depending on which definition that you use. Both would be biased. So our survey measures density in 20 to 275. We apply that estimate of density to the shallower and deeper areas, even though it's likely not correct, which was certainly shown in Area 2A this year. But if we do the opposite and to only use 20 to 275, then we're not giving areas credit for having bottom area in those shallow and deeper areas where there are, in fact, halibut. So it affects apportionment more so than it does the coastwide data set, and that's shown in the fourth bullet point there, where the influence, there's two different model runs that you'll see. The estimate of E-bio at the end of the model run ranged from 288 to 292 million pounds, depending on which combination of bottom area and whether or not you used the WPU adjustments you used. And on the other model run, the variation was from 254 to 262 million pounds, so just a difference of 1 or 2%. So these factors, again, don't matter much in terms of the model output. For the coastwide estimate of E-bio, they do have a bigger influence on apportionment. Pause here a second. Okay. The current halibut assessment model was developed in 2006, 2007, and has remained unchanged since. We do fit variants to it. So we say different models, we don't really mean different models. They're different model runs, different model variants. It's the same basic model, which has as a key feature, feature is the right word, size-based selectivity. It's flexible in the sense that there's, as you'll see, there's a lot of different switches you can turn on or off, different aspects that you can change to look at the impact on the estimate of E-bio and spawning biomass. Typically, we've done 5 different variants or 5 different runs. For the past several years, our recommendations have been based on the variant called trendless. And most of these models, at least the first 3 models, the main difference among them is how we treat survey catchability, known as Q. I have a definition on the bottom of what Q is. It's simply a scalar or a multiplier or a scaling factor between how many you catch as a rate on your survey and how many then you estimate to be in the population. And that Q is typically has a value of 1 over several million. So for each one that you catch in the survey, you estimate then there are several million in the population. But it's an influential parameter. The survey Q may vary, it may not vary. It certainly has annual variability, but in the model you can fix it or you can allow it to vary. You can also allow it to have a trend or not have a trend. We've selected the trendless model the past several years using the argument that we go to great lengths to standardize our survey, same date, same time of the year, often same time period, same bait sizes, everything. So there'd be no a priori reason to expect survey Q to change. But of course, Q can be affected by many things, the environment and so on. What we call the vanilla model was to fix within any particular model run survey Q so that it wasn't allowed to have any variability whatsoever, though when you ran at different years that fixed value would actually change. So it's a little bit incorrect to say that it's constant. It's only constant within a 1 year's run. And then what we call the wobble SQ model is that survey Q is actually allowed to drift, allowed to have some trend over time if the model wants to go there. So survey Q could be increasing or decreasing over time. And then just sort of to round out the set of models that are run, we've got ones that we call sort of a NIMS type, where it's not fitted to the commercial WPUE data, and then a Cajun model where we don't fit it to the survey WPUE data. So we can statistically compare these different models and also give you some insight into what survey Q looks like among different models shown here. The statistical comparison among these models is in the column labeled, that's a delta AIC. This one with the lowest value is the preferred model statistically. And as has been the case for the past several years, Wobble SQ does actually fit the data the best. It's a value of 0. Despite that, we've gone with the trendless model because the trendless model tended to be very close. The only other model that really fit nearly as well. And its difference, if you look at the past several RARAs, was in the order of 4 to 10, something like that. This year, though, wobble SQ actually fit considerably better, and that's the main basis. That plus the fact that we do understand that the model's been overestimating biomass, and the wobble SQ is a more conservative estimate of eBio. The value out of the wobble SQ is 260 million pounds. The eBio estimate out of trendless was 288, and you get some idea there then of the difference in the survey Q and how that varies among the models. The dark blue one is the base, or the trendless, that actually has zero slope. The dashed green one doesn't come down as much, indicates somewhat higher Q at the end, hence the lower eBio estimates, and so that actually has a trend a little bit greater than zero over the length of that time series. Again, this is the assessment model as it is, flawed or not. This is what we get from it. Estimates on the left of age 8 recruitment, the 87, 88 year classes are to the far left. We know the 87, 88 year classes were quite strong since they showed up in our age samples. There were some years in which the 87 year class by itself comprised 50% of the animals that were captured. The model estimates, again, in large measure because of the decreased, the relative constancy of catch numbers, but the smaller size at age, large numbers are relatively strong year classes from about 98 forward, although relatively large error bounds in those estimates. The right-hand plot shows the trends in 3 different measures of biomass that you've heard a lot about. eBio in the gold triangles, spawning biomass in the red diamonds, and total biomass in the blue circles. Each of these has shown retrospective behavior. The horizontal line there is just showing that for the first time now in the last several years, the total biomass at any rate is now estimated to be lower than the value it was in 1996. It's not been the case for the past several assessment runs. So this is a measure. This is at the interim meeting. We spent probably too much time talking about uncertainty. This sort of captures it in one slide. Model uncertainty or structural uncertainty. Wang spent a great deal of time talking about a different kind of uncertainty, which is more of a bias, retrospective bias. This is simply illustrating one of the other measures of uncertainty that we have, and that's for any given model. How much uncertainty is there in there? And so what I've done here is I've shown those crosshatches are given that model and the chosen parameterization of that model, the confidence intervals around the eBio and the SBio. So the eBio is measured horizontally. You look at the one that's dark black, that's for the base or trendless model, the one that has been the basis of the catch limit recommendations the past several years. And if you recall, that eBio estimate was 288 million pounds. The 95% confidence interval ranges from 250 to 300 something. And then the female spawning biomass is indicated on the vertical axis. That was around 350 million pounds. The 95% confidence intervals, you can see that there. And then the dashed ones with the crosshatches are the other 4 other model variants or model types, and you can see their estimates, relatively speaking, of eBio and SBio and confidence intervals. The 16 other little circles there are attempts that I was making when I was trying to diagnose the retrospective behavior of the model, different things that I tried, things that switches I turned on or off, parameter values that I changed. I put in a doubled estimate of bycatch. I changed the emphasis values and the likelihoods. A number of different things here. I don't need to go into them. But you get some idea just from changing single switches with 4 given model how much that affects the model output. So you can see there's a wide range there from the chosen model and its parameterization to, again, the variability that you see just by changing one single thing in the model. That's with the focus on the trendless model. The next one shows the same thing, but with the focus now on the wobble SQ model. And you can see the same sort of thing. So there's a broad range there of values tending to cluster around the model that's the focus, but there's still, as you can see, a strong amount of variability. And among all these different things, we tended to be more towards the size of 260 million pounds. And I also have to note that I've not found the source of the retrospective behavior yet. I'll have more about that in a minute. But anyway, it was informative to try these things, but it didn't solve the issue with the assessment model. So this is the model output as measured by the reference points that we do each year. We take action on the last data point, as Juan illustrated. The earlier values in these trajectories differ now than what they did at the time the assessments were run. At least we've used this model now for the last 5 years. But the model output presently estimates spawning biomass to be at 42% of its unfished value. The unfished value shown there at the top, that's an estimate of how many of the biomass of females that would be in the ocean in the absence if you were to stop fishing, let it build up, how much would be there. And through a lot of work over history, people develop reference points on what you aim for to keep your female spawning biomass above, and that's been, in our case, at least above B30. The right-hand plot here shows similar information along the horizontal axis. The dashed vertical lines relate to B20 and B30. The vertical axis looks at harvest rate relative to your target. Our target's been somewhere between 0.2 and 0.25, changing over time, and different definitions of eBio. And the blue dot then is the estimated current status of the spawning biomass and the target harvest rate. It's in what we call the OK quadrant. Spawning biomass estimated to be above the minimum where you take action. Target harvest rate higher than desired. There's a better quadrant to be in, of course, and there's a couple of really bad quadrants as well. Here's the model estimate now of the current and recent composition by age of the and weight of the exploitable biomass. The front row of this matrix would be the contributions to the eBio as beginning of 2012. The largest component of the exploitable biomass is going to be age 13, 12, 13, and 14 age halibut. Those strong year classes of 98, 99, 2000 finally coming to fruition, if you will. They're predicted to be large beginning several years ago. They now are the largest part of the exploitable biomass. You can contrast that, their contribution to exploitable biomass with what occurred 15 years ago when the 87 and 88 year classes marched through time. Those year classes were numerically strong, but they had the advantage of being much, much, much larger at age. And so for any given similar number of animals, their much larger size means that their eBio contribution was much larger. As you can see, even this plot will show you that the eBio nowadays is quite a bit smaller than it was back in those early days. That's eBio. This is and that was in millions of pounds. This next one is two different displays. The other two different types of biomass we illustrate. Total biomass is again shown in a similar plot to the eBio, only now the vertical axis is in millions of halibut instead of millions of pounds. And I highlight the same strong year classes. And again, this is what the model shows. You look at the ages 6, 7, 8, 9, 10. It estimates large numbers of those animals in the population, too small to catch. They're not components of the exploitable biomass, as you saw. They're almost minuscule, but they're there in large numbers, as estimated in the model. And then the female spawning biomass age composition is illustrated in the bottom left-hand corner. Simply the effect of the act of fishing truncates the female spawning biomass. Juan had a plot on that showing the decline in the ratio or how many females are in the population, but to the extent possible, you want to maintain a broad age distribution. And on that measured on that basis, we're pretty much okay. It hasn't changed a lot over the past 10 years. We still have 20-plus-year-old females, 15 and older, but they don't comprise a large component. The bulk of it comes from ages 13 to 15 or 12 to 14 or so. So we get estimates now, new estimate this year of the different types of biomass. And again, I don't need to go over this too much because Juan showed it, but this is the estimate now of the harvest rate on the exploitable biomass by area. We do this by taking the coastwide biomass, estimating the distribution by, or the apportionment by area using the survey WPUE. And so we can then go back and look at, based on removals divided by exploitable biomass, estimate what the realized harvest rate was. And it was this growing realization in Area 2 in particular, that the closed area models just did not match what this kind of arithmetic did that motivated the move to a coastwide assessment. And so in that regard, it has been effective in bringing down the realized harvest rates in Area 2. They've come down, as you see, strikingly in some areas, though given the retrospective behavior, perhaps they've not come down as sharply. The one question we needed to answer is people said, well, how can you catch 80% of the halibut in Area 2 and have any left? Because the harvest rates that we show is defined as a fraction of the exploitable biomass taken, but the total biomass is much larger than the exploitable biomass. Other work I've done in past years showed that the exploitable biomass is somewhere between a fifth and a tenth of the total biomass, and it's decreasing as the size of the age decreases, so that at the height of the high harvest rates in Area 2, if you measure harvest rate as a proportion of the total biomass of ages 8 plus or 6 plus, it was quite a bit lower, anywhere from 20 to 15 to 25% measured against those other biomasses. So revision and retrospection. This year's assessment, as I noted, was affected by two things. One, the late arriving, and it's not just commercial data, well, it's principally commercial data. It's also some age data, I believe, gets entered late. But it lowered the commercial WPUE. And that alone had the effect of revising or lowering the estimate of eBio for the beginning of 2011, on which catch limit decisions were made, from 318 million pounds down to 292 million pounds. So had we had the full data set and run the thing, done everything the same as last year, we would have made a decision based on 292 instead of 318. So that was an 8% decline. This year's data, this year's model run, further revises the 2011 estimate of eBio down to 245 million pounds, which is another 17% down. So that would have been the basis of the catch limit recommendations. And that's a larger factor than the revision. So it's retrospective behavior, which you've heard a lot about. We've had it in different forms, in different types of models for halibut, going back to Cajun. It's waxed and waned for 20 years. Bill Clark spent a lot of time looking at it. In 2009, there was an indication that it actually had kind of waned there. And it went, not entirely, because we still reported on it, but it kind of went off the radar screen a little bit. The last 2 years, it's definitely waxed, and hence the big focus on it this year and the lengthy presentations about it and the implications of that if it were to continue, or if we don't change how we do business in terms of changing the model, fixing the model, or doing it some other way for determining catch limit recommendations. This is not unique to us. The retrospection occurs in groundfish stocks here, particularly on the East Coast. We've had a large number of them there. There's been a working group out there that's been working on this for a long time. They had a big report come in a couple years ago, and I just take one quote out of there that they had, where they examined a number of methods to determine the source of a retrospective pattern using simulated data, but they couldn't do so. There's no diagnostic tool that says, well, here it is. It's the age data. It's the weighting and the likelihood. It's the, you can say it tends to be due to either something in the model or something in the data. It can be model misspecification, trend in some parameter, trend in selectivity, trends in catchability. It could be, contrary trends in your data. One goes up, one goes down. The model doesn't know which to follow. It could be unspecified mortality. There's a trend in mortality that's not being captured by the data that you get. It may be that there's simply so much, and our model fits a lot of data. There's so much inertia, there's so much data there that the model doesn't move quickly. And as long as the biomass is going down, you're going to get revisions downwards. When things turn around and going up, you'll tend to lag the actual biomass estimates, and the next year will go upwards. So this is going on, and as Juan talked about, it does suggest that one way of dealing with this immediately, if you believe it's going to continue, that the level that we see this year is going to be duplicated, is going to project, is to adjust the applied target harvest rate. So to give you an idea of what the retrospective behavior looks like in those two different models, the trend list that's been used for the past several years and the Wobble SQ as of this year, you can see there's been this progressive downward revision of the biomass trajectories. It's similar to both. In fact, I did this for all the different model variants, and it's a very similar picture. All the different type of models that I had tried show the same behavior, of relatively similar magnitude. And the way these biomass trajectories revise downwards is by adjusting the year class strength estimates. So you get early large year class strength estimates, they revise downwards as you get multiple views of them. And then you can see here they've been tending to decline in the order of 6 to 8% each year. You can look at the most recent ones, where there's only 3 or 4 years of data. You don't see that downwards thing, but again, those are the most poorly estimated. It's hard to see whether or not that's going to project forward or not. That's simply what things look like as of this year. Our close cousin, if you will, Sablefish, dealt with a more modest but similar in some ways retrospective behavior and their assessment they had for a number of years. I show the output here from the 2008 model where you see each subsequent year revise the biomass, in their case total biomass, downwards, and then last year I believe it was, they cured it. It was through dropping one time series and some reweighting, I think, of something in the likelihood. Anyway, they were able to correct that behavior. I'm not saying that it's going to happen to ours. We don't know what's going to happen with ours. They don't have that that feature of ours, that uptick at the end, which is not a good feature, particularly because it is perhaps overly optimistic. Just note that their cured behavior didn't drop the final data points by another some odd percent. It was simply stabilized around that value. Just a few other considerations to think about, things that I think about, we think about in staff here. This to me is the elephant in the room. I mean, because selectivity is such a crucial thing. The fact that animals at any given age are still smaller in each subsequent year, it's got to be influential, and it's occurring not just at the larger ages, which part of the larger ages could be explained by the fact that you are size selective fishing. So, at some equilibrium status, you're going to have smaller animals, just because you're cropping off the bigger ones. But this is going on at the younger ages as well. I don't show it here, but I don't think I do. The trawl caught animals, which are much even younger than this, the size at age is dropping. Why that's occurring is the great unknown, and I think it'll be a highlighted research topic for us. Tim Lower has written a white paper on this, sort of outlining some of the possibilities for why this is going on. Is it driven by the fishery? Is it driven by ecosystem considerations? Bill Clark and I did a paper where we found a strong correlation with the number of halibut in the population. But we didn't consider about the number of arrow-toothed flounder in the population, which is 5 times the biomass of halibut. There could be a genetic effect. You're cropping off annually all the bigger animals. Are you removing from the gene pool those animals that create other big animals? We don't know. I mean, nothing sticks out hugely. We've decreased some harvest rates, seen a minor uptick a little bit in some size at age in some areas, but it's not been huge. These are just enormous differences, and I would really like to know what's driving this. And this is the longer-term perspective. Just zero in a little bit here on shorter time frame, get a better view here, get an idea that these are still dropping across all ages, and these are not minor declines. So, we've been going downwards here for 15 years, and I just want to let people know that we have not sat still during this. We've each year as we come to here, and trying to figure out what's going on, we've taken some action. I just want to remind people here, that some of the things that we've done trying to get behind this ongoing decline. We established, with the harvest policy, this threshold limit reference points, which we felt that we'd take action. You might remember the conditional constant catch harvest policy Bill Clark and I had, and that you rejected soundly immediately because it would have capped total removals. It may not have been so bad in hindsight. In 2006, we made the big switch to the coastwide model because we knew something was out of whack in Area 2. We began in 2006 on concern over some ongoing trends out west. Started designated areas of particular concern. Began in Area 4 CDE, where we dropped the target harvest rate there. There's some, after we had it's called a CIE review, a Center for Independent Experts review of the current assessment model and harvest policy. That's why we kind of stuck with that model till now. And one of the things that they suggested we do is consider the effect of retrospection on spawning biomass and how you might react to that's going on. We took a look at that. Didn't change anything, but we did have some look at that. We dropped to a 50% harvest rate in area 4B, and then 4A, and then 3B. We changed slow up fast down to slow up full down. You know, these catch limits and total removals, we've dropped 7 consecutive years. The total removals have been down by 40% since 2004, and that'll be by 50% if you accept the 2012 catch limit recommendations. And actually, that's since 2004. Actually, the bulk of these reductions have been in the past 3 to 4 years. The catch limits, for the commercial catch limits, they're down by 46% since 2004, and it'll be up to 57% if you accept the 2012 catch limits. Just comparing here the estimates of exploitable biomass between, you know, I take the trawl data, apply a selectivity curve to it, and try to compare what the trawl survey thinks is out there in terms of exploitable biomass and what the assessment estimates there from the coastwide biomass with the survey partitioning. You've seen these comparisons before. They're in the blue book. They're not bad for Area 4. They're less good for Area 3, and they're miserable for 2C. But again, 2C, I don't think that's a highly trawlable area. Certainly, the trends are very similar. The trends are captured. There could be, you know, a number of reasons for the difference in the vertical scale, from different selectivities, different estimates of natural mortality, and so on. The one thing that I want to look at, the one independent estimate we have of halibut in the ocean is what we see in the NIMS trawl survey. So there's 3 different sets of data here. I'm going to look at exploitable biomass in numbers, total biomass in numbers, and then unexploitable biomass in numbers. The third one just being a subtraction of the second from the first. So this is trying to put in one graph areas 4CD at the top, down to 2C at the bottom. The NIMS swept area estimates of first exploitable biomass. So that's taking the selectivity curve and applying to the total biomass and total numbers. And you see the downward trend I said. I made these, I know you can't read the horizontal axes, but I think they're in the blue book. They go from the period just before the beginning of our survey in 96. So usually just go back to 93 or 94, and then they go up to the most current survey. So they tend to span that period 94, 95 to 2011. You see the decline there in exploitable biomass and exploitable numbers, unquestioned that's been going on. The story's a little bit different for total biomass and total numbers. And I think this is where the, you know, our feeling that there were still at least some fairly large numbers of halibut out there. They're just small. So E-bio is going down, no question. But the total numbers, you know, these would indicate relatively stable, relatively level numbers over time. Probably an increase in area 4 CDE. It's particularly by numbers. You look at the early days of 4 CDE to the total numbers, what there is now. I know 2 years ago when 3B, 3A came out, the estimated numbers of halibut was the highest ever for the Gulf of Alaska. It came down this year. As I say, those trawls were highly variable. But as of 2 years ago, though, there was near record numbers in area 4 CDE according to this trawl survey, and there were record numbers in area 3A and 3B. You know, it hasn't moderated too much. It's moderated a little because of the trawl survey this year, but as a gross picture, you can see that this is the other view of halibut in the ocean. And then I see the third one here is simply taking exploitable biomass and exploitable numbers and subtracting them from total biomass and total numbers and giving an idea of the trend in small halibut. These are ones then that are not available to the directed fishery given the current size limits and selectivity patterns. I'm not going to go through these at all. Area by area would take too long. I've been showing this now for several years. It's just a one-stop shop for indicators about each area. I'll just use 2 areas as an example. We talk about you have the removals time series there, the different types of abundance indices, the raw survey WPUE, the adjusted survey WPUE, and the estimate of the coastwide assessment biomass trends for that area. Get an indication of the ages of males and females in survey catch on the right, and below that the ages in the commercial catch as well. Surplus production, which is an indicator of how much you can take from a stock and maintain a constant biomass. When surplus production exceeds removals, you should have an increase in biomass, and when surplus production is lower than removals, you'll have a decline. And then the time series of commercial WPUE and the amount of effort shown there. And I'm just gonna page through these here. Just takes a minute to do here. VA, B, 4A. All right, one more. And so this is I believe my last slide here. We'll talk about apportionment. There's a lot of numbers available. They're on the Blue Book for the different means of weighting the input data, whether you accept or use the survey WPU adjustments, which we've done now for the last few years, which bottom area definition is used. Two different models, the trendless model, which has been the basis of the catch limit recommendations for the past several years, as well as WAPL SQ, which is what we recommend this year. The current harvest rates, the adjusted harvest rates from the output of Juan's work, and then we look at what would be the realized harvest rates, depending on which advice you followed, and what we estimate would be the actual realized harvest rates.
Thank you, Stephen. Well, this will be the shortest of all our morning presentations. May not have the best news, but it will be the shortest.